Okay, I'm going to have a go at blurting gravity to help you with your gravity past paper. So the idea, I'm going to write down everything I can remember, and you're going to at least once see if you can recreate this sheet of paper or sheets of paper without looking. So first of all, we'll start off with definitions. So we've got gravitational field strength, and that's the force per unit mass on an object at a point in a field, or the force on a 1 kilogram object. And then we've got gravitational potential, which is the work done moving 1 kilogram from infinity to the point in the field. Now, you might also see it as minus the work done moving 1 kilogram from the point in field to the infinity. The point is it's a negative number. If you go from infinity to the point, then you're decreasing the object's energy. The object's doing work on you, so we get a minus answer. And then we've got potential energy, which I don't tend to do, but I think it's important actually, which is the work done moving an object from infinity to the point in the field. I'm just slightly annoyed because I'm getting a very slight rattle. How annoying it is for you from this. Must be something I can do to stop it rattling. But then you'll be more annoyed by, I'll just try putting my laptop resting on it. Right, we'll see how we get on. And then we can start looking at the equations. So we've got Newton's universal law of gravity, which gives us the force of gravity between two objects. M1 and M2 are the point masses. R is the distance, must never say radius, between the point masses. G is the universal gravitational constant, 6.67 times 10 to minus 11. F is the force in newtons, and it's the force on both objects. So if Earth is pulling down on me with 980 newtons, I'm pulling the Earth up with 980 newtons. We've got G is equal to Gm over R squared. Field strength either has newtons per kilogram or meters per second squared, is G, the mass of the object causing the field, and then the distance to the point mass causing the field, or if it's a spherical object, the distance from the point in the field to the centre of the object. And it either tells us the force per unit mass, or as it tells us the acceleration due to gravity at that point. And then we've got V is equal to minus Gm over R. So this is the potential in joules per kilogram. Again, universal gravitational field constant. Distance from the point to the centre of mass of the spherical object, mass of the object. We've got the work done moving between 2 points in a field, and I'll do a bit more about this in a moment, is M delta V. And we've got the potential energy is the potential, the energy per unit mass, times the mass of the object in the field. So that then becomes Gmm over R. Notice the energy ones are over R. That's not on the date sheet, so if you want to use it, you're going to have to memorise it. And field strength is force per unit mass, so it's defined as force over mass. Might be good if you were doing this to actually write down exactly what everything stands for, rather than just saying it. Then moving on, we're going to talk about a bit around kind of orbity type stuff. So first of all, in all orbits, we're saying that the force of gravity is equal to the force required to make it go in a circle. We sometimes say it without the little m's. The acceleration due to gravity is equal to the centripetal acceleration, and that gives us the velocity, say, of a circumpolar orbit satellite. Or we can say gm over r squared, m is m r omega squared, and this works much better for both Kepler's third law and geostationary orbits. Omega from the circular motion section is 2 pi f, which is 2 pi over t. So we can say that gm over r squared is equal to omega squared r, which is 2 pi all squared r over t squared. So I think what I'm going to do now is cross multiply, and you get gm t squared equals 4 pi squared r cubed, and then you could rearrange that for t to find the period of a geostationary orbit. You can rearrange that for r, find the radius of a geostationary orbit, or t squared is proportional to r cubed, which is Kepler's third law. Then we need to understand about the energy of satellites. So if we can imagine two equipotentials, say minus 50 megajoules per kilogram, and this will be a less negative number, minus 30 megajoules per kilogram. If we want to know how much energy is needed to move an object from here to here, then work done is m delta v, and doing it strictly with the signs, the work is, so let's say this is a 20 kilogram object, and then the change of potential is always final, so it's minus 30 minus 50, which is 20, so it's 400 megajoules needed is the work done to move from here to here in a field. These are equipotentials. These are points of equal potential. The field lines will all be coming in like this. And every time, so these show the direction of the force on a mass. The closer they are, the stronger the field. And where they cross a field line, when an equipotential crosses a field line, they're always at right angles. And then we've got two sorts of orbits. If this is the Earth, we have circumpolar orbits, which you should write. I'm realising we've made quite a long video already, so I'm going to stop. So that's going over the poles, and because the Earth's spinning underneath it, it will go over every point on Earth. It can be low, so it can take more detailed pictures, and it can be used to take pictures of weather systems or land surveying or spying. Or we can have a much wider radius orbit, which we would get from here, a geostationary orbit. So it has a period of 24 hours. It is in the same plane as the equator. Okay, so plane means flat shape, so it has to be directly over a point on the equator and same direction as the Earth's rotation. Okay, so what I want you to do is see how much of that you can reproduce in one go from memory, and then add in the bits that you've missed by either you could have copied this down to start with, or you can just go back through the video. But you need to keep checking, and you need to keep doing that. But hopefully that will save you time on the questions. Okay, thank you. Bye.